Okay, hi everybody. Sorry for my voice. I lost my voice during the conference. So my name is Diman and I'm a researcher at Hewlett-Packard Labs. And today I'm going to talk about our paper SmartNIC at the Edge for transient compute elasticity. And we are going to show how we are going to harvest SmartNICs compute for offloading edge workload spikes. So the growth of edge computing systems is being driven by solutions and applications that require high performance and low latency, such as Internet of Things, manufacturing, and other operational technologies. Also, edge applications are increasingly adopting serverless framework, but provisioning for additional computing needs on demand, or what we call it is, as we call it in transient elasticity, is non-trivial. So SLA violations occur due to workload bursts. SLA violation occurs due to workload bursts and short-term compute power shortages on edge servers. So there exists uncertain transient spikes which can cause SLA violation. And there are violation penalties, and the penalties for these violations are very high. So we have penalties for these violations, and the violations occur due to workload bursts and short-term transient spikes on edge servers. So this figure shows the CDF function of average CPU utilization of Microsoft Azure's dataset in 2019. And while the average CPU utilization is low, but the P95 percentile of the CPU load is higher than 60% when we have 60% of the VMs being used. So we have uncertain transient spikes which can cause SLA violation, and the penalties for this violation is high. And since SLA violations have very severe penalty, one common way to eliminate the violation is to over-allocate the resources preemptively. So right now, what the infrastructure capacity management is being done is that once we have some transient spike, we over-provision the servers and we add an extra server to the system. So what you will end up doing is that you over-provision the resources, and then whenever there's high transient spike, then you are going to use the extra resources that you have provisioned. But this way we are over provisioning and we are wasting the useful resources in the system, which also adds a lot of cost, and it's not energy efficient at all. And meanwhile, there are SmartNICs which are gaining popularity to offload workload and different network functions, and they provide real-time line rate at scale. But the additional general purpose compute of the SmartNICs has largely been untapped, because the SmartNICs have been mainly used for network function and for faster packet processing. But what is not sort of used is the augmented memory and also compute resource that is on the SmartNIC. And by the way, the SmartNICs are much cheaper in terms of the cost compared to adding an extra server. So in this project, we want to find the answer to this question: that can we design an architecture that can dynamically handle the sudden spikes on demand and address the transient elasticity and optimally allocate the compute resources? So in spike offload, which is our framework, we try to answer this question. The first challenge is that we want to guarantee application SLA. And in this project, we expose application-specific metrics to the scheduler. And also, we want to distribute the traffic according to the service rate of each node. For example, if there's transient spike, one of the servers might not be responding very well. So we want to have a scheduler that is aware of such transient elasticity. And we work on a queuing-based approach that distributes the traffic according to the service rate of each node. And then we have a workload prediction module that predicts the spikes before the actual load arrives in the system. And this is our system architecture. The major components of our solution consist of three parts. The first part is configure the traffic distribution. So we are using a queuing-based approach to distribute the traffic. The second solution is a workload prediction module that predicts the spiky workloads. And the third one is the spike management module that tries to change the workload distribution whenever there's a spiky workload. So here I'm going to show you a demo, a very short demo of how our system architecture looks like. Well, before I go to the demo, let me show you the testbed setup. So this is our testbed setup. So we have 2 servers. On each server, we have a NVIDIA Bluefield 2 SmartNIC, and then we are deploying a Kubernetes cluster on all of these 4 nodes. Themis 2 are the servers, and then we have 2 Bluefield. And then we are deploying an open-fast serverless platform on top of the Kubernetes cluster. And then we are sending the HTTP function request to the API gateway, and then we distribute the traffic here. So let me show you quickly the demo that we have. So you can see here we are deploying a Kubernetes cluster of 4 nodes. We have 2 servers. On each of the servers, we have a Bluefield node, and we can deploy them as a server or a worker node. And then we have the deployed the OpenFast framework. And as you can see, we have deployed here a Fibonacci function that computes the Fibonacci. And then this is the Kubernetes dashboard. You can see all of the nodes on the Kubernetes dashboard. And then we have deployed the Fibonacci function as a pod in the system. And then you can, for example, invoke the function using the OpenFast UI. And what we do is we first try to send HTTP requests of like thousands of Fibonacci function. And then we try to see what is the response time when we run it only on the host. And this is the response time distribution when we are running it only on the host. Now, if we add some extra workload and add a spiky workload to the host, we can see that. So we are running a stress tool to add extra workload on the host, and then we try to run the same workload and then see how the results will change. So you can see the cores are being utilized 95%, and then once we run the workload again, you can see the response time distribution function changes. So it takes some time. Maybe I can move it a little bit too. Yeah, here is the response time when we have extra transient spike on the server. So we run it on the same server, and then the red figure shows when we have extra transient spike running on the system. The blue one is when we don't have any background workload. And then after that, we deploy our Akida, our smart offload architecture here. We have the Akida script running, and then we run the workload on both the SmartNIC and the server, and we distribute that traffic according to the service rate of the nodes in the system. So once we deploy that, we run the same workload, and then here is the result when we are running it on both of the nodes, and then we distribute that traffic accordingly. So this was the short demo, and let's take a look at the impact of the Akida architecture when we run it with different functions. So we have deployed 3 different functions. There's the Fibonacci function, there's a key value function, and then the sentiment analysis, which is somehow a machine learning function that we are running. So we run it on 3 different cases. The first case is when we have a background workload on the first server. The second one, which is the pink one, is when we add an extra server. One of them will have the background workload and the other one doesn't. And then we use also the same traffic distributor as the spike offload that we had. And then we have the spike offload with 1 SmartNIC and also 2 SmartNIC in the system. And as you can see, by running the workload on the SmartNIC, we are somehow the same as adding an extra server while we have a lot of costs. And also we are reducing the SLA by 20%. And then we also look at the performance divided by cost. So we are looking at 3 functions. And because the SmartNICs are lower cost, not just in terms of CapEx and OpEx, but also in terms of energy consumption. So if we divide the performance divided by energy, you can see that the spike offload is doing much better in terms of energy saving as well. So to summarize, we looked at spike offload, and we showed that when we have transient elasticity, we could use the SmartNIC to offload some of the workload, and our solution was threefold. We had the traffic distribution module, we had workload prediction, and then we leveraged the SmartNIC for managing the spike, and we showed that we could reduce the SLA violation by 20%, and also we could improve performance divided by energy by 2x. So some of the next step is looking at distributed machine learning, and then schedule the DAG-based workload when we have multiple functions running, and they are in a sorted as a function chain. We are also looking at anomaly detection and predicting the resource requirement and optimize workload placement. So thank you for listening. And by the way, we are hiring, and if you are interested in intern or full-time position, please come and talk to me. Thank you. Any questions?